Okay, so in the last class, I have explained about the features of the amplifiers here. It is what are the features of it is direct coupled and all that, and also that RC coupled amplifier, the arrangement of the circuit of the RC coupled, and what is its frequency response. Okay, all that has been studied in the previous class. Okay, and in this class we are going to study about the concept of the AC load line. Okay, already the concept of the DC load line so has been studied here. What if the line is drawn between it is two endpoints, it is VCC comma 0, and the one more point is equal, it is the 0 comma, it is VCC divided by RC plus RE. If the line is drawn, it is acting as the DC load line there. Okay, and in the same way, so that we are going to see the concept of the AC load line. So in this class, we are going to study it is what do we mean by it is a large signal amplifier, and about the concept of the AC load line, and AC and the DC equivalent circuits of the given circuit, and what is the phase inversion, and what is the actually AC load line, and also the classification of the power amplifiers. Okay, all this is going to be studied in this class here. Okay, and in this case, what do you mean by it is the large signal amplifier? So if you take it is what the large signal amplifier are designed to amplify the large input voltage signals, or it is going to switch the heavy load currents as would find is driving in the loudspeakers, etc. So in the last class, I think it is what the definition of the small signal amplifier and an example RC coupled amplifier has been studied there. So that if you take the small signal amplifier, the input is applied in terms of the it is very small in terms of the microvolts. In the same way, if you take for it is large signal amplifiers in which is used to amplify the large input voltage signal, it is going to take the input which is of the large, and again it is going to be get amplified. Okay, such type of amplifiers are called as it is large signal amplifiers. And if you take the concept of the AC load line, okay, so already you know about the voltage divider bias circuit. Okay, it is considered it is common emitter amplifier configuration under the voltage divider bias. So in a transistor amplifier, what this DC source sets up the quiescent current and the voltages, and the AC source it is going to produce the fluctuations in these voltages and the currents here. So that you can able to see this circuit, it is already explained in the previous class. This is the voltage divider bias okay circuit, and it is also the arrangement of an RC coupled amplifier also. Okay, so this is of the BJT. RC is the collector resistance, R is the emitter resistance, and R1 and R2 are the biasing resistors. It is to be connected at the base, and what this CS and the CC are the coupling okay capacitor. It is one is connected at the input in order to give the connection with the input, and other is to be connected towards the load or for the next stage here. And it is what this plus VCC is the DC voltage, and what this V in is an AC voltage. So in order to analyze the any of the circuit, it is to be analyzed for the DC voltage available, and also the AC voltage available across it. So for that purpose, the simplest way to analyze the circuit is to split the analysis into two parts. One is the DC analysis and another one is the AC analysis. So in this transistor amplifier, what happens, what this DC voltages, it is used to maintain the operating point. Already I think you know that in order to use the BJT as an amplifier, its operating point it should be in the active region. In order to maintain the operating point at the middle of the active region, so that we are using the DC voltage sources as the biasing voltages. And the AC voltage is nothing but the actual signal is to be get amplified, and according to these voltages, it is going to give you the amplification here. It is going to fluctuate the currents and the voltages. Okay, so it is to be get analyzed for the DC and as well as for the AC. So initially we'll see the DC analysis. It is the DC equivalent circuit. Okay, suppose if you take the DC equivalent circuit here, it is for this one, it is having the certain rules here. So he is asking to reduce all the AC voltage sources to the zero. So if you want to do the calculation, it is for the DC, all the AC sources is to be made as the zero, and open all the capacitors, so that you can able to see it is one is at the input side, other is at the output side, and one is the bypass capacitor. So all these capacitors used to be acting as an open circuits, and it is with this reduced circuit the DC current and the voltages can be calculated. See here, so that so as per the condition, in order to obtain the DC equivalent circuit, he is asking the first point as AC voltage source to be made as the zero. So the input voltage V in is in terms of the AC, so it is made as the zero, and afterwards he is asking to open the capacitor. So it is going to be get opened means it is, so it's not having the connection with the input. In the same way, if the output capacitor, if it is also to be open means, so the collector is not having the connection with the load or for the next stage here. And in the same way, what this bypass, this emitter is not having the connection with the ground here if it is to be get open. So what this circuit is to be indicated with this way. This is with the BJT, RC, RE, R1 and the R2, and the DC voltage is to be considered. So this is assumed to be the DC equivalent circuit. It is for the circuit considered. Okay, it's only one example circuit here. Okay, so if the capacitor has been opened means, so this entire part is going to be, it is deactivated. In the same way, if this capacity is to be, it is to be get open means it's not having the connection with the load here. So it is also to be neglected here. So you can consider only the VCC R1, R2, RC and the RE. So this is VCC R1, RC, R2 and the RE, and in this way the circuit is to be considered. In this way, so that you can obtain the DC equivalent circuit. And in order to obtain the AC equivalent circuit, the exactly opposite process. So it is for an AC equivalent circuit, he is asking to reduce the DC voltage sources to the zero, so that you can able to see what this plus VCC is the DC voltage. It is to be made as the zero, and he is asking to short all the capacitors. So in the AC equivalent circuit is asking to short the capacitor. What this capacitor is to be, okay, short circuited, acting as an on switch, and it is also to be short circuited on switch, and it is also to be shorted. And what this circuit is used to calculate the AC currents and the AC voltages. Okay, so it is exactly opposite, so that you can see in the DC equivalent circuit is asking to reduce all the AC voltage source to zero. In the same way, in the AC equivalent circuit is asking to reduce all the DC voltages to zero. Exactly opposite. In the DC equivalent circuit, he is asking to open all the capacitor, but in the AC equivalent circuit, he is asking to short all the capacitors. In this way, so that you can obtain it is the DC circuit, and in this way you can obtain the AC circuits here. So if you do the arrangement according to the rules means, is asking to reduce the DC voltage to, okay, the zero means it is to be made as the zero means it is to be get connected to the ground here. And in the same way is asking to short the asking to short the capacitors means it is to be short circuited here. So that you can able to get the circuit as in this way. So this is input voltage, it is to be connected to the series resistance, and it is to be connected with the base here. So this is an input AC voltage, this is an RS, and it is to be get connected to the base here. And in this case R2 is to be connected for the ground, so this R2 is to be connected for the ground here. and the R1 is been connected to the VCC. So it is, but according to the condition, what this DC voltage is made as the 0. So it is to be get connected to the ground. So indirectly it is to be connected to the ground here. So this R1 is to be connected for the ground here. In the same way, this RC is also to be connected to the ground. So in this, RC is to be get connected for the ground here. And what this RL is to be short circuited means what is along with the so along with the collector, it is to be connected for the ground. So along with the collector, it is to be connected to the ground. And in this, you can able to see what if it is to be short circuited, what this ammeter end is to be connected for the ground. So this other end of the RE is also connected to ground. So this RE is to be neglected. So it can be omitted. So what this ammeter terminal is to be connected for the ground. So in this way, so the AC equivalent circuit has been obtained from the circuit considered. Understood? So it's very simple to remember. If you want to obtain the DC equivalent circuit, all the AC voltages is to be made the 0 and opening all the capacitors. In the same way, if the AC equivalent circuit is to be obtained, all the DC voltages is to be made the 0 and all the capacitor is to be short circuited. Okay, in this way, the AC equivalent circuit and the DC equivalent circuit can be obtained. And now we'll go for the phase inversion. Okay, it is because of the fluctuations in the base current, it is collector current, and the collector voltage are also swings above and it is below the quiescent voltage. The AC output voltage is inverted with respect to the AC input voltage, meaning it is 180 degree out of phase with the input here. Okay, see here, it is whatever the input has been applied here, it is for an AC input, it is for the base, it is whatever the output obtained across the load here. Okay, it is collector, it is having an 180 degree phase shift output voltage. Voltage is going to be 180 degree phase shift. So that if you consider the input voltage as an VBE, if you apply the input as the sine wave, the IP and the IC is equal to the same, and in this VCE is an output, it is having an 180 degree phase shift. If you want this, you can see for the positive half cycle, output will be the negative half cycle. In the same way, for the negative input, the output will be the positive. VBE is the input voltage which is applied in between the it is base and the ammeter here. So the input voltage is considered to be as an VBE, and the output is obtained across the collector here. It is collector and the emitter. So this output is to be considered as an VCE. So in this way, it is going to undergo the phase inversion here. Understood? So in case of the large signal amplifier, if you apply the input at the base of the transistor, the output obtained across the collector is having 180 degree phase shift. So that means that output is out of phase with the input. It is for the positive half cycle of the input, the output will be the negative half cycle. In the same way, for the negative half cycle of the input, the output will be the positive half cycle. In this way, it will be continued here. This is about the phase inversion. And if you take the AC load line here, so that already you know about this graph here. It is the graph of the voltage VCE versus the IC current. The voltage VCE is to be considered along the x-axis, and the IC is to be considered along the y-axis. And if you draw the line, it is from the point VCC to the VCC by RC. This is acting as of the DC load line. It is already studied in the previous classes. And if you take what this point Q, this is an operating point. It is to be represented exactly center of the active region, at which the input will be completely amplified, and at the output you can get the amplified output of the full signal. It is without the clipping, and what this point is to be called as an ICQ, and it is what this point is called as a VCQ. And if you see the another line which is indicated with the green color here, this is an AC load line here. Okay, so it is when considering the AC equivalent circuit, so the output impedance becomes RC in parallel with RL, which is less than the RC plus RE. It is while calculating the equation for the DC load line, already it has been simplified in the previous classes that you obtained. It is what is IC is equal to, it is minus 1 divided by RC plus RL or RE. But in case of the AC load line, if you do the AC analysis, in this you can able to see here the RC and the RL is assumed to be in terms of the parallel here. And if it is to be in terms of the parallel, so the impedance is to be considered after simplification of this parallel combination here. So for that purpose, this output impedance becomes RC in parallel with the RL. It is assumed to be, it is less than the RC plus RE. So in the absence of the AC signal, okay, this load line passes through the Q point. If the AC input is not available, means it is going to pass through the operating point Q here. So it is therefore the AC load line is a line of the slope, it is minus 1 divided by RC in parallel with the RL. It is passing through the point Q, so that you can able to see what this line in terms of the green color. It is it has been, it is moved, it is near to the, it is a saturation, and in which the impedance is RC in parallel with the RL has to be considered, and it is going to take the shape as in this way here. Okay, so under this condition, what is Q point is not in the middle of the line, so that you can observe very carefully. So it is not exactly, it is middle for the AC load line. So what this Q point is selected, okay, slightly upwards means it is slightly shifted to the saturation side here for the AC analysis. This is about the AC load line here. Okay. So I'm going to repeat in brief. It is once again. It is what this large signal amplifier is going to take the input of the large voltages, and the concept of the AC load line is to be dependent on the AC voltage applied and also the DC voltages applied. So it is to be analyzed for the AC analysis and also for the DC analysis in order to obtain the AC equivalent circuit and the DC equivalent circuit. In order to obtain the DC equivalent circuit, so all the AC voltage sources is to be made the zero and all the capacitor is to be made open, and in this you can obtain the DC equivalent circuit. In the same way, in order to obtain the AC equivalent circuit, all the DC voltages is to be made as the zero and all the capacitors is to be shorted, and you can obtain the AC equivalent circuit as in this way. And if you take the phase inversion, if you apply the input at the base of the transistor, that is whatever the output obtained across the collector is out, it is 180-degree phase shift. So that means that output is out of phase with the input with the phase inversion here. So that if you draw the AC load line, if the circuit has been considered as in this way, in the AC, in the DC equivalent circuit only RC is considered and RE is to be considered, RC plus RE. But if you take the AC equivalent circuit, RC in parallel with RL is to be considered here. So for that purpose, instead of considering the RC plus RE, for the AC load analysis, it is going to considering the output impedance as RC in parallel with the RL. So if you take the slope of this line, which is equal to minus 1 divided by RC in parallel with the RL, under which the operating point is not assumed to be at the middle, it is near to the saturation here. This is about the AC load line. And if you take the classification of the amplifiers, so the classification of especially power amplifiers. So what this power amplifiers is mainly classified into the, it is 5 types. It's class A, class B, class AB, it's class C, and the class D. Okay, so that if you take the class A, it is going to conduct for the full cycle, which is equal to 360-degree. So if you apply, it is entire full cycle. It is a half cycle for the positive and half cycle for the negative. It is going to give the conduction for it is both the cycles. And so entire full cycle, entire 360-degree, it is called as of the class A. So what is the circuit diagram of the class A, and it is what is its efficiency, what are its applications, all that is to be studied in the next class. Okay. In the same way, if you take the class B amplifier, it is going to conduct for the half cycle. It is going to do the half operation of the class A. So, but if you see the efficiency wise, it is having the more efficiency. So, if you take the class B, it is going to conduct only for the half cycle, which is equal to only for 180 degree. If you take the class AB amplifier, it is in between the A and the B. In between the A and the B means it conducts more than the half cycle. It should be less than the full cycle. So it is slightly more than the 180 degree and it should be less than the 360 degree. If it operates in between 180 and it is 360 degree, it is itself is called as the class AB amplifier. In the same way, it is class C amplifier is going to conduct for it is less than the half cycle. It is to be less than the 180 degree means it is class C amplifier. If you take the class D amplifier, it is used for on off, it is for the non-linear switching. So it is not dependent on an angle. Either it is to be operated in the cutoff region or in the saturation region. According to that, it is going to act as the class D amplifier. So it's very easy to remember. If you take the class A, it is going to operate for the full cycle of it is 360. The class B, it is half cycle for the 180 degree. The class AB in between the A and B, so it is more than a half cycle. It is to be less than the full cycle. In between 180 degree and this 360 degree, the class C means it should be less than the half cycle. It should be less than 180 degree. And if you take the class D, it is used for on off. It is non-linear switching. This is about the classification of the power amplifiers. And all of these amplifiers, okay, circuit diagram and its efficiency is to be studied in the next classes. Okay. So if you take the possible, okay, the sample, it is a descriptive questions. It is based on the syllabus which has been covered in this class. Is he may ask you to define the large signal amplifier, and he may ask you to explain the concept of the AC load line. It is with the equivalent circuit and the phase inversion, or he may ask you to just give the classification of the power amplifier. So all these are the possible questions, okay, of the portions covered in this class. Okay. So this is all about the concept of the AC load line and the classification of the power amplifiers. And in the next class, okay, the entire detailed of the class A, it is the power amplifier, its circuit diagram, its efficiency, all that is to be studied in the next class. Okay. Okay. Thank you very much.